Hey, what's up?
I'm well. How are you?
Good. All right. Hopefully this recording makes it through. So I want to talk about today. So we're going to start today talking about the venerable Kahn-Ingold Pralog nomenclature system. And let's get oriented here. Essentially, what this is going to allow us to do is to, talk and describe the configuration of molecules with respect to their stereocenters. So, okay. So if we bring back the example we've been working with, this this alcohol. Okay, we said those two molecules are related because they are enantiomers of each other. They are non-superimposable mirror images. And we need a way to specify which enantiomer we're talking about. And that's where this nomenclature system comes in. Relatively straight, the rules are relatively straightforward. It's the sort of execution once you establish priorities that often confuses students. So we'll work on that. So essentially what this nomenclature tells us to do is to prioritize the substituents on the carbon using numbers 1 through 4, okay? And hey, Bob. And so the rules for the prioritization are not super complicated. The first thing is that atoms with the higher atomic number get higher priority. Okay. And so we look at the substituents and we say, okay, which atom has the highest atomic number? That's going to be sulfur. So that's number 1. Fluorine is number 2. And oxygen is number 3. And if you have a hydrogen attached to a stereocenter, it's always going to be number 4. Okay. So that's the prioritization. And then we need to translate that into what we call the R or S nomenclature. And so the way this is done, and this is the kind of the tricky part, is that you reorient the molecule so you're looking down the carbon and the carbon lowest priority substituent bond. And so we're going to make a Newman projection where we look down that bond. So looking like this. okay? And so I can basically start out drawing as I do a normal Newman projection. Okay, so this will be the carbon, and we're looking from C to H. There's nothing else attached to H, so we don't draw anything in the back, and the H is understood in this context to be directly behind the carbon. And then we need to place the substituents in the right place, in the right orientation, and this is where it gets a little tricky. And so to achieve this perspective, I'm going to rotate the molecule sort of about the vertical axis, okay? And so when I do that, again, let's start with what's easy. The OH is up, and that's going to remain up, okay? And then the fluorine swings off to the right, sulfur is on the left, okay? And so if we then 3, 2, 1, put our priorities there, okay? Once you generate that image, you then essentially connect the numbers with a arrow, so like this. Okay, so I go from the highest priority to the lowest with my arrow. This arrow runs in a counterclockwise direction. And so if the arrow runs in a counterclockwise direction, that means this is the S enantiomer, okay? I can play this, I can do this exercise for the other enantiomer. Maybe it's worth doing. So I'll just draw, we'll have a little inset over here. Okay, and so again, we'll do the prioritization. So sulfur is 1, fluorine is 2, oxygen is 3, hydrogen is 4. Okay, and then remember, you must look down the bond between carbon and the lowest priority substituent to do this properly. So we need to reorient as we did before. And we'll draw a Newman projection looking down that bond. In this case, I'm rotating about the vertical axis, sort of going from right to left, okay? I can put the alcohol in, the OH, because that is on top and that will remain on top. Then I need to think about the remaining 2 substituents. The fluorine gets rotated off to the left and the sulfur ends up on the right. We add the priorities again, 1, 2, 3. We draw a line or draw an arrow from 1 to 3. That runs in a clockwise direction. And so that is the R, what we call the R enantiomer, okay? So the absolute configuration of a stereocenter is always described by this RS nomenclature, okay? And in the simple cases where you have 4 different substituents, you simply prioritize by atomic number, okay? A good way to remember this is that, you know, if you draw an arrow and it runs clockwise, it's sort of going off to the right. And so that is the R enantiomer. That's how I remember it, okay? S goes to the left. All right, so so if I go back here, I can just say this is the S enantiomer, this is the R enantiomer of that molecule. And so why is this helpful? It's helpful because the absolute configuration matters, especially in biological contexts. And we want to know, we want to be able to describe that absolute configuration in a way that's unambiguous and concise. So what happens when you run into substituents that have the same, the elements of the substituents are the same. So let me go to another deck here. So okay, so if two atoms have the same atomic number, you're essentially going to continue outward until you find a difference, and using that sort of atomic number, looking for differences in atomic numbers of the substituents. So again, best illustrated with an example. Okay, so in this example, I've got 3 carbon substituents attached to the carbon. Okay, but you can tell me right away those 3 substituents are all different, and so I have 4 different substituents at the carbon center. So this is probably an asymmetric carbon. I just need to figure out how to prioritize those substituents to tell you which is R or S. And start with what's easy. So H is the lowest atomic number, so that's going to be lowest priority, number 4. And then we need to differentiate the carbons. And so because they're all the same, because they're all carbon, we have to look further. Okay. And what we can see is that the substituent in the back, that carbon, which I highlight in green here, is attached to 2 other carbons. Okay. And so that is the highest priority substituent. The one coming out towards us is only attached to 1 other carbon, so that's number 2. And the methyl group, of course, is not attached to any, so that's number 3. Okay, so hopefully it's intuitive. You sort of look to see what has, by atomic number, the biggest groups appended to them, and that's how you prioritize when you have the same element. And so again, if I want to go through the actual assignment, I look down the carbon, the bond to the lowest priority substituent, so that's the hydrogen. In this case, to draw the Newman projection, I'm going to rotate like this. And what I end up with is an orientation like this. And so again, the methyl group on top, that doesn't move, so we just drop that in, okay? And then the number 2 substituent in the front, which is called an ethyl group, is going to swing off to the right. And so that now is over here. And the remaining substituent that's going into the plane, into the board, is going to come forward and wind up on the left. And so that is and so then I just copy my numbers over. So 1, 2, 3, draw my arrow. And so this is the S enantiomer of that molecule. Okay. So the examples I've given you are sort of the easier cases to deconvolute because the hydrogen has been going off to the right in the plane of the board. The ones that are trickier is if you reorient the molecule such that the hydrogen's coming out at you or going up. There you have to do a little bit more maneuvering to get the correct Newman projection. And so I'd encourage you to practice this through the problems on sapling. And it's very helpful if you're getting stuck to have models in front of you, build out the carbon as you see it in the line wedge diagram, and then rotate that model to make the Newman projection. The There are two other rules that come up less frequently, but they're important. So the third one is dealing with double or triple bonds. Okay, and these essentially are going to count as in duplicate or triplicate. And so another example would be here. Okay, so I've got 3 carbogenic substituents. Each of them has 2 carbons. And so how do I prioritize them? And the way to do it is to count the double bonds. So the CC triple bond is interpreted by these rules as being a carbon attached to 3 carbons. And so that's priority number 1. The double bond is interpreted as a carbon attached to 2 carbons. That's number 2. The ethyl group, CH2CH3, that's a single bond as it's drawn, and then the hydrogen is 4. Okay. And so we can draw a Newman projection for this, and I'm just going to swing it again around the vertical axis. So the hydrogen is going back. And the double bonded substituent is on top. The alkyne, the triple bond is on the right. And the ethyl group is on the left. Add the numbers, 1, 2, 3, draw my arrow. It's going counterclockwise. And so this is the S enantiomer. Okay. And then the final rule has to do with isotopes. And this really doesn't come up very often, but the book has it, so we'll include it here. Okay, so in the case where you have 2 isotopes of the same element attached to a carbon, the higher molecular weight one gets priority. And so, for example, if I had this molecule here where I have deuterium, which is an isotope of hydrogen, we prioritize using rule number 1. So fluorine is 1, alcohol is 2, and then between the D and the H, the D wins because it's higher molecular weight. So 3 and 4. And then if I do the rotation, draw the Newman projection, pencil in the priorities, draw the arrow. That's counterclockwise, and so that is also the S enantiomer. Okay. So, so a couple comments before I move on. The RRS nomenclature has no correlation whatsoever to where these things are located in space, because we're relying on the molecular weight or the atomic weight of the elements. They could be anywhere, and so you can't, basically don't try to like derive any shortcuts. Like you have to go through this this nomenclature system to arrive at the correct descriptor. Okay. The other thing I would say is that, again, dealing with this issue that you have to look down the bond to the lowest priority substituent, this can be a little bit tricky. For example, when the hydrogen or the lowest priority substituent is going up. So Okay, so for example, same molecule, the hydrogen is up. It's the same absolute configuration. So this is also the S enantiomer. But to get this properly oriented, I need to look down that bond. And so I need to flip the molecule up. So you need to pay attention to where that substituent is in the way that it's drawn and make sure that you rotate the molecule to the Newman projection in the appropriate way. Okay. All right. So RRS is a descriptor. It's like cis or trans. It tells me the absolute configuration of a stereocenter. When we're talking about enantiomers, the thing that's very interesting about enantiomers is that they have identical physical properties. So same melting points, same boiling points, same spectroscopic data. So if you take an NMR, an infrared, or an optical or not, and a UV vis, you get the same data. But they do differ in one physical property, and this is a little obscure, but it's important. And so they rotate plane polarized light in different directions. All right, so okay. So you're probably sitting there thinking, what the heck is he talking about with plane polarized light? So let me do a quick explanation of what that is. I refer you to figure 6.6 in the text, which is going to give you a much better drawing of than what I'm about to show you. So normal light consists of oscillating electric and magnetic fields. We only concern ourselves with the electric field. And in a normal sort of unpolarized light, that electric field is oscillating in all planes. And so if I draw a plane here and represent the electric field with the squiggly line, it's rotating in that, it's oscillating in that plane, but it's also oscillating in the plane that's perpendicular. Okay, so let me make this another color. Okay, and it's oscillating in every single plane. All right, again, this looks like pretty bad. Please look at the figure 6.6. If I take a cross section of this, we can show those oscillations more clearly. So I've got my black oscillation going up and down, my red one perpendicular, and then of course there is, I haven't shown it on the left, but there's everything else in between. Okay, like sort of an infinite number of degrees. And so that's what we call unpolarized light. The light is oscillating, the magnetic field is oscillating in every single possible plane. We can, by using various filters, generate what we call plane polarized light, which is, you can conceptualize these as sort of, essentially vertical slits that we pass the light through, and only light in one plane can get through. So So this one's much easier to show. If I take light that's unpolarized and say pass it through a very, very narrow vertical slot, what would emerge would be light that is plane polarized, so only oscillating in one direction. And I can represent that here sort of in 2 dimensions and then with the cross section on the right. And so what's interesting is that chiral molecules will rotate plane polarized light when you pass it through a sample, okay? And enantiomers will rotate plane polarized light in opposite and equal directions. So let me show this graphically. So
Are you still in need of typewriters? Oh, sorry.
always, yeah, always. Yeah, thanks. I have 7 chickens at home. They're buff Orpingtons. If you don't know what a buff Orpington is, you may look it up online. Buff is actually the color. They're like these bright orange or yellow orange chickens, and they're very intelligent. They're constantly laying eggs. And my students will occasionally bring me empty egg cartons. And they have names, but that's for another class. So enantiomers rotate plane polarized light in opposite directions, and the magnitude of that rotation for each enantiomer is equal, okay? And so if I wanted to show this schematically, I would draw my plane polarized light traveling along, and then I'd have what I call a cell. So many of you have probably done UV vis spectroscopy. You know, you put your sample in a cuvette in solution. It's the same idea here. We make a solution of our chiral molecule and put that in a cell. And so like I can draw our old friend here. Okay. And we shine the light through that cell. And what happens when I come out the other end is that the plane has been rotated. So if I draw 2 planes here, now the light might be oscillating like this, okay? So the plane gets rotated by the sample, okay? And this, I've drawn it as approximately 90 degrees. I'm not trying to imply it's a 90-degree rotation. That's easiest to show, obviously. It can be anywhere from 0.1 degree to actually greater than 360 degrees. It's the magnitude of the sign, the magnitude of the optical rotation is very difficult. You cannot predict it sort of from first principles. There are ways to actually calculate it, but there's no useful qualitative, model to predict. So we don't know what it'll be. We don't know which direction it'll go in. We don't know how big it'll be, but there will be some amount of rotation. Caroline, did you have a question?
Yeah, if you put a racemic mixture in the quote unquote cuvette part, would no rotation occur?
Exactly.
Or would not even?
Yeah, I'll come to that in a few minutes, but the answer is exactly. So if you have a racemic mixture, so a 1-to-1 mixture of enantiomers, 50.0% to 50.0%, you can imagine that one of those enantiomers is going to push the light in one direction. The other enantiomer pushes it back by the same magnitude, but in the opposite direction. And so the net effect is that you don't get any rotation. And so this is actually diagnostic for a racemic sample. So like you can have a molecule that has stereocenters, you go take an optical rotation, you see that it doesn't rotate the light, and so you know that you've got a one-to-one mixture of enantiomers. Yeah, it's a good question. Okay, so so let me just add the cross sections here because this might help with this. So like if you imagine, you know, here's the plane polarized light coming in, and then it hits the sample, and then it's going to leave with something that's different. Okay. And so there are two sort of variables here. Which are the direction of rotation and the magnitude of the rotation. And so there are two ways that the light can be rotated. We can rotate counterclockwise. And then, of course, I can rotate clockwise. Okay. And so a molecule, again, we're going to just have a sort of an arbitrary descriptor here. This isn't related to anything. This is not something we can directly relate to structure. It's just, you know, we're observing a phenomenon here, observing a property. So a molecule that rotates plane polarized light in a counterclockwise direction is what we call the levorotary enantiomer. Also represented as just the minus sign in parentheses. And if we rotate light in a clockwise direction, it's dextrorotary. Also represented as a plus. Okay. And so your enantiomers are either plus or minus, dextrorotatory or levorotatory. There's another descriptor that's less frequently used, but sometimes they'll just call this the L enantiomer, and this is the D enantiomer. Okay. And so one enantiomer of your molecule is going to be the plus one, the other is going to be the minus. The other thing that we're interested in is this degree of rotation. So the extent to which the plane rotates is defined by what we call alpha. And alpha is the observed optical rotation. Okay. And, you know, if we just jump back for a second, I don't know what's going on. I'm losing my whiteboards. And as I said, the recording on the last one was messed up. This is semi-annoying. Okay, let me just redraw it real quick. So we're going to shine the plane polarized light through a sample. Sample is here. Okay, this is, you know, my sample and solution of molecule. and it's going to come out and be rotated in one way or another. Okay. And so, I've got a physical, solution of the sample after that incident light. And so you might expect intuitively that the degree of rotation, the magnitude of rotation is going to depend upon the concentration of the sample. And then also the path length, the sort of the length of the cell. And that is the case. And so Caroline says, just to confirm, no correlation between RNS and plus and minus. That is absolutely correct. There is no correlation. And that is because plus and minus are a physical property. The RNS are just this arbitrary nomenclature that we made up. Yeah. Okay, so so the observed optical rotation alpha is an experimental, is what we measure, and then we say that it is equal to alpha in brackets, and this is what we call the specific rotation. Times concentration and concentration is usually expressed in grams per milliliter, and it's just kind of the way it is. It's kind of unfortunate because it's not, we use molarity, nowadays. This is sort of an anachronism, but it's always expressed in grams per milliliter, and the L is the path length in decimeters, so 10 centimeter increments. So, you can imagine as the concentration goes up, the observed optical rotation is going to increase. As the path length increases, the observed optical rotation will increase. Okay. And just as a little side note, you guys are in the department that has the most powerful polarimeter in the world. And so this was developed by Professor Pat Vaccaro. And the idea is that he wanted to be able to measure optical rotations in the gas phase. Obviously, the concentrations are very low there. And so you need a very long path length. And he engineered a series of mirrors such that you get a path length on the order of, I think, several miles in this sort of benchtop polarimeter. And so that amplifies the observed alpha value. All right, so anyway, so alpha is the specific rotation. You can think of alpha as an extinction coefficient. If you've taken, hopefully you've seen that, when you do UV vis spectroscopy, the extinction coefficient is this property of the molecule. It's how intensively it absorbs light, right? Alpha is the same thing. It's a property of, or specific rotation is the same thing. It's a property of the molecule. It's different from molecule to molecule, okay? But we can back calculate the specific rotation just by rearranging. So we have alpha over CL, and that is an important equation, okay? So why is this useful? So as I said earlier, an optical rotation of 0 tells me that I've got a racemic sample, assuming that I've confirmed that the molecules themselves are chiral. But we can also, if we know the optical rotation of pure enantiomers, we can calculate then the enantiomeric excess of a sample. So let me like thinks this is whiteboard 6, and there's actually, this is 5. So let me see Christine, what was your question there?
Oh, the equation that you had written with the the equation that you wrote before. Oh wait, I just saw it. You just rearranged it. Never mind.
Yeah, I just rearranged it.
Sorry.
So the alpha without any brackets is what we observe. The alpha in brackets is the specific rotation that's a property of the of the molecule. And so another way to say that is that the specific rotation is the optical rotation corrected for concentration and path length. Okay. So anyway, so we can calculate EEs using optical rotation. So say, for example, I've got this molecule. And it's an enantiomer. Okay. And we know that the specific rotations of these molecules are, let's say, 20 degrees. Okay. Okay. And again, this would have to be experimentally determined. I'd have to have access to pure enantiomers. You could have access to just one of them and then go measure it to know that. Okay, but let's say we knew that, and then I came along with a sample that I knew was a mixture of these enantiomers, but I didn't know the ratio. I didn't know which one was favored or which one was more abundant, and so. Okay, so say I took that sample of unknown composition, measured the optical rotation, and got a value of 10 degrees. EE is very easy to calculate. The enantiomeric excess is simply 100% times the alpha of the mixture over the alpha of the pure. Okay, and we're going to assume C and L both equal 1, so I don't have to apply any corrections. So this would just basically be plus 10 over 20, which equals 0.5 times 100% is equal to 50%. So that would be 50% EE. Okay, so what exactly does that mean? It means that I've got 75, for every 100 molecules, I have 75 of this one and 25 of the other one. Okay. And so you could imagine, we can sort of think through this intuitively. If I had 100% of one, I'd expect to see an optical rotation of 20, right? If I had a 1-to-1 mixture, the optical rotation would be 0. And if I'm at 75-25, I have essentially 25 molecules of one enantiomer canceling out 25 of the other. And so I'm left with sort of 50 over 100, or half of what I would expect for a pure sample. And so I observe an optical rotation of 10. Okay. And so this allows you to back calculate the EE of a sample. It used to be, back in the day, this was how it was done, without exception. In practice, there's when you're trying to do this on small samples, milligram quantities, it can be very difficult to accurately determine concentrations. And there are other analytical methods that are more accurate and amenable to small scales, such as HPLC, which have sort of replaced polarimetry, but it still gets used. And it's if you can sort of work within its limitations, it's a very fast and unambiguous way to determine EE. All right, so in the last couple minutes, I just want to work our way up to diastereomers, and I'll leave diastereomers for the last, for Friday's lecture.
Sorry, can I ask a quick question? before
Yeah,
you
go
move on?
ahead.
How do we know that we have 75 of the enantiomer on the left side and 25 of the
Oh, because the,
other one for every 100 molecule of the other?
yeah, because the final optical rotation was the optical rotation of the mixture was positive.
Oh, okay, thanks.
Yeah. All right, so just want to say a couple comments about asymmetric centers. We're not limited to carbon, okay? Anything with 4 substituents can in principle, 4 different substituents can in principle form an asymmetric center. And so, for example, ammonium salts, okay? So suppose I had this ammonium salt with 4 carbon ligands attached to it. If I draw this in space, and I'm just placing the substituents in arbitrary locations. Okay, it would look something like that. And I can, of course, draw an enantiomer for this molecule. Like that. That nitrogen is close to tetrahedral. You can't interconvert those 2 mirror images without breaking a bond, without sort of reconfiguring the molecule. And so that nitrogen is chiral, or an asymmetric stereocenter. The molecule is chiral. Okay. There's actually a whole field of synthetic chemistry where we actually use these chiral ammonium salts as catalysts to achieve different transformations. So this is an ammonium salt. The nitrogen has a formal positive charge. If you just consider an amine, which is neutral. So okay, so I have 3 substituents on nitrogen. There's also a lone pair. I can draw that in like that. And so this technically has 4 different substituents. And so if I want to, I can draw this with the line wedge representation. And I can draw a mirror image of this compound. I'm going to leave some space here in the middle. Okay, so that's the mirror image. Those are, technically enantiomers, but this molecule is not chiral. And the reason it's not chiral is that that nitrogen can invert. Okay, via planarization. So it goes to sp2 hybridization and then flips over. It's like, it's like an umbrella blowing over in the wind back and forth. And so, so amines, even though they have 4 substituents, are not in fact chiral. You can't lock them in one conformer at room temperature. Okay, so other molecules that have lone pairs but are chiral, for example, are sulfoxides. So sulfur does not readily invert at room temperature. Okay, now if you heat these things, you can make that happen, but we basically define the threshold for chirality at room temperature. So is it configurationally stable at room temperature? For sulfoxides, they are. So you can have an enantiomer of that. The other one that's very common are what we call phosphines, which are the phosphorus analogs of nitrogen, just going down the periodic table. These also do not invert at room temperature. Therefore, they are configurationally stable and chiral, and you can have RRS enantiomers. Okay, so this is kind of an aside. We're not going to ask you to. We certainly will not put up other elements and ask you to tell us if they're chiral or not. But it's good to know that sometimes you can have chiral molecules with lone pairs and they're configurationally stable. Other times they're just not. Okay. All right, so I'm going to stop there. We'll take a 5-minute break. We'll do office hours. Friday's lecture will cover diastereomers, and we are going to start the chapter hopefully on cycloalkanes. And this is a very important chapter. It's very interesting. Hopefully, be intellectually satisfying too. There's a lot of really interesting features of cyclic compounds that hopefully you'll find very exciting. But so please, let's take the time to read through the text and familiarize ourselves as much as possible before you watch the lecture, so you can watch it over the weekend. All right. Anyway, I'll stop there. I'll do office hours in 5 minutes.